Okay, so we continue with our treatment of cross sections that are not as simple as you've managed in the previous classes, in the previous class in stacks. So as a summary, the theory that we know how to apply to compute stresses, that is how to go from moments to stresses, has been such that the principal axes of the cross section must be known. At the present time, you have the ability to calculate the principal axis in cross sections that have one axis of symmetry. Why is that? Because if there is one axis of symmetry, you already know that one principal axis is the axis of symmetry. And the other principal axis, which is must be perpendicular to that. So in the worst of circumstances, like this one, you might not know where it is with respect to distance, although you do know in this case that it is horizontal. But there are cross sections for which we do not know the orientation of the principal axis a priori, okay? And for those sections, we need to be able to determine the principal axis orientation. Now, the text assumes, for some reason, that the computation of the principal axis is kind of like a special thing or something. So in the homework problems, the principal axis most of the time are given what their orientation is. I think that's too much of a babying. So we're going to learn how to compute the orientation of the principal axis and to understand where this thing comes from. So imagine, so let's call this principal axis. Okay, so we have a cross section which is arbitrary in shape. We will say that this is the centroid, and for our discussion we will have an xy axis, horizontal and vertical, which is our reference. Of course, that's arbitrary. And we're going to say that the principal axis happen to be rotated, and they are x prime and y prime. Our task, and the rotation is an angle theta measured from the x-axis counterclockwise. Okay? So our task here is to determine what is, or to find the formula for theta. So if you look at an arbitrary point here, well, first, okay, let me delay a bit the physical reasoning while I put this notation in here. So this is an arbitrary point in the cross section, and that point, when measured in this set of axes, is y prime up and x prime to the right. And when measured on the xy, it is y up and x to the right. Okay? So we have x and y and x prime and y prime. The distance from the origin to the point, this one, we're going to think about it as being d. And the angle that that line makes with the x prime axis, we're going to call it phi. Okay? You know what? It's not too bad, but I'm going to do it again because I want it to be very clear for you. Okay? So I'm going to take the whole board over on this side, let's say, make this thing even bigger. Here is the axis, and here is the rotated axis. This is x prime, this is y prime, this is x, and this is y. Okay? This right here is an arbitrary point. That point has that distance, which would be y prime, and has this distance, which would be x prime. That point is at a distance d from the origin, which is the centroid. So these are centroidal axes. And the angle with the rotated set is phi, while the rotation of the set with respect to the original is theta. The coordinates of the point in the xy axis are just simply y, which is this, and x, this x prime down here, which is this. Okay? That tells everything. Now, let's assume that we had a moment about the x prime axis. Say we had a moment about the x prime axis. Because the x prime axis is a principal axis, the stresses that would be developed in this cross-section would be such that the resultant would give a moment only about x prime and nothing about y prime. Okay? Now the stress at this point, sigma, is equal to mx prime, right? Multiplied times y prime, the distance, my, divided by ix prime, right? That would be our simple formula, my over I, in which this is simply the principal axis and we just apply it in standard fashion, right? Now, what I'm saying, and this is the key point for you to try to understand as well as you can, is that all these stresses which are getting generated in this plane, right, compressions and tensions and so on, when you sum moments about the y prime axis, they must be zero if, in fact, this is a principal axis, because that is the definition of what a principal axis is. When you apply a moment about it, you just get curvatures in that direction and the resistance about that moment, about that axis. So, in other words, we can apply this formula because the moment was about x prime. If this was not a principal axis, I would not be able to use this formula. Okay? Now, y prime, let's see. No. So what we want to say is that the condition for a principal axis is that the integral of that stress sigma multiply what is the moment of that stress about the y prime axis, is that stress times dA, which is a small force that takes place here, multiplied times the distance x prime. That over the full area, if we do that integral over the full area, if that is a principal axis, then that integral must be zero. Okay? Now, if we substitute the formula for sigma, then we have that the integral over the area, mx prime, what do we do with y prime? Nothing. We just put y prime. What do we do with ix prime? Nothing. We put ix prime, so that's our sigma. Then this is x prime, and then this is dA. And we're saying that that must be zero. Now, mx prime at this cross-section is a constant, and ix prime is a constant. So if this is equal to zero, it obviously has nothing to do with these constants that could be taken outside of the integral. And so what we find is that the integral of x prime, y prime, dA must be zero. When integrated over the area. This right here is what defines that you have a principal axis. If your axis is a principal axis set, then if you take all the points and you sum their products of x times y times dA, you will get zero. If it's not a principal axis, that is not true. Now, for those of you that may be not following, well, not following, but let's say just to make it even clearer. Let's say that we have this cross section. For this cross section, we know that this is an axis of symmetry. This is one material, and this is another axis of symmetry. So these are the principal axes, right? Now let's see, why is it that for those axes this is 0? Let's say that you take this point here, and you're going to do this integral. But you're going to do the integral numerically. Just think about what an integral is, just the sum of things, right? So let's say you take that point, which happens to be, let me use numbers to make it really clear. Let's say it happens to be 3 to the right and 5 up, right? So the contribution of that little thing, which is a dA in area, to this integral is 3 times 5 times dA, right? Now, in order for us to cancel that one, we just need something which is 3 and minus 5 in dA, right? So if I look at this other little square down here, which happens to be at 3 and at minus 5, and it has the same dA, then these two will cancel, right? And you can see that for any square that I take, on the upper part, there will be one in the lower part that will cancel and make this sum 0, right? Therefore, when I do it over the complete cross section, I get nothing, indicating that this is a principal axis, okay? Now, if we take I don't know, a cross section like this, all right? Let's say the centroid is here, and let's say we look at x and y. And we want to see if those are principal axes. Well, if you take a look at this point here, this little square, which happens to be at some value of x and some value of y, for example, 4 and 2, to cancel it, you would need something at 4 and minus 2, right, for example, and at 4 and minus 2 there's nobody, right? You could also cancel it if you want to say by minus, what is it? By minus 2, yeah, minus 2 and 4, or minus 4 and 2, right? So you could also say over here, but you don't, there's also nothing over here. So it is evident from the argument that we made on the previous rectangular case that this one does not immediately tell you that the IXY is going to be 0. That is, that integral will not be 0. And in fact, it just turns out that for a section like that, the principal axes are not horizontal and vertical. Okay? The principal axis will prove to be tilted. So for a situation like this, it may prove to be that this being the centroid and this being x and y, you have to have the axis maybe like this or something, so that it turns out in the end that when you do this integration, for every little piece, you multiply this times that little area, and then another little area, this times that area, and so on, and then this one, which is this, and so on, add them all together, that you do get 0. Okay? So, the integral of x prime y prime dA being equal to 0 is the condition for the set of axes to be principal axis. Okay? That's the condition for the set of axes to be principal axis. Now, needless to say, there's no way that we're going to try to find what the principal axes are by just trial and error. I mean, you could, if you got infinite time, start tilting them, and doing the calculations numerically until you find something that is zero. But we want to do something better than that, right? So what we want to do is we want to develop the relationship between what is actually no. Let's put it this way. This is what I forgot. I should have said at this point. Let's define the property Ixy as the integral over the area of x times y times dA. Okay, that's called the product of inertia. So let's define the integral of x times y times dA as the product of inertia. And let's say that what we want to do now is to find out if I know the product of inertia about some set of axes. Let's say, for example, that I was able to calculate it about x and y. I did it one time. Can I find out what it would be if I rotate this a certain amount without going through and just doing the whole thing from the get-go? That's what we want to do, because if we can get that formula, then it will be easy to make the formula equal to 0 to find what the orientation of the principal axis are. So that's our task now. So we're going to derive it as follows. We're going to say Ix prime y prime would be the product of inertia about the rotated axis, right? And Ix prime y prime will be, by definition, the integral over the area of, since we're working with this set of axes, it would be simply x prime times y prime times dA, right? I think that should be clear to you. Now, the following trigonometric relations are rather apparent. Y, which is this, is just d times, wait a minute, y, yeah. This is an error. What I meant is phi, please correct this. Phi is the angle that the point and the origin make, but not with respect to the x prime, but with respect to the x. Okay, it's the total original angle, and theta is the rotation. Now, under that condition, then, y is just d sine of phi, right? And x is just d cosine of phi, correct? Now, we can also write that y prime, this, is equal to d times the sine of this angle, right? But that angle is phi minus theta, right? So you can see that y prime is equal to d times the sine of phi minus theta. And likewise, x prime is equal to d times the cosine of phi minus theta. Okay? From here, we can say that, let me see. Okay, so what I'm going to do is the following. We're going to take this expression here that says y is equal to d sine of phi, and we're going to solve for d. So from this expression, we're going to say d is equal to y over sine of phi, right? And from this expression, we're going to get another one that says d is equal to x over cosine of phi. That's obviously true. Now, if that is the case, then we can come here and say that this is the integral over the full area of x prime y prime dA. So we're going to get x prime, which is this, but instead of d, let's write x over cosine of phi, right? That's x prime, d, which is x over cosine of phi, times the cosine of phi minus theta. That was x prime. Now let's write y prime. So y prime is d, but instead of d, I'm going to write y over the sine of phi, and then times the sine of phi minus theta, and then dA, right? All right, need some space to keep things clear. So let's see, where do I get some space? Do I need this anymore? Probably don't need this. If I do, we'll have to repeat it. But, so I'm going to write this Ix prime y prime here for you, which is the integral. I'm just copying, but with a little bit more organized way. X times y, so that's that x, that y. The denominator is sine of phi, cosine of phi. And in the numerator I have sine of phi minus theta times the cosine of phi minus theta times dA. Right? That's x prime y prime. So we can take that off, because that's just what I copied back with a little more organization. Take this off. And so we are at that point, right? Now, you see we have this sine of phi minus theta, and we have this cosine of phi minus theta. Now, you can go to your trigonometric relationships if you don't remember them, as to what is the formula for the sine of the difference between angles. And the sine of the difference between angles is